Okay, Chem 7, this is Julie, and we're going to talk about chemical reactions in this set of lecture. So remember, when we have an acid or base, it breaks up into pieces. If it's an acid, it will give off an H+. So this is dissociation of hydrochloric acid, and it's giving an H+ off. A base is going to accept the H+, so hydroxide is a good example of a base. It takes the H+, and it makes water. And a salt is what we make when we have an acid and a base reacting together. It makes a salt, and a salt is an ionic compound. Remember, ionic is from an element from the left side of the periodic table and an element from the right side of the periodic table. So when a generic acid, any kind of acid, so this is just the symbol for any acid, it has H+ normally, then it ionizes, which is also called dissociation, and it makes the H+ pop off, and then the rest of the molecules over here. So you have the H+ positive, and that shows you have an acid, and then you have the negative part of the molecule. Strong acids are going to do 100% of this. So once you throw this in water, you're going to have all of it break into these pieces. So there's going to be none of this left over here. Weak acids are going to have some of this in the beaker, some of this in the beaker, and some of this in the beaker container. So base is the opposite. It will take the H+ from the acid and incorporate it and turn it into a molecule. So bases accept or take that H+. Water can act as a acid or a base, and in this case it's with a strong acid, so hydrochloric acid is really strong, and this H+ pops off, it jumps onto the water. So this is the before picture, this is the after picture. So afterwards there's just a Cl- left over, and then that extra H went onto that water, and now it's called hydronium ion. Water can act as an acid or a base depending on who he's paired up with. So in this case we have a base, ammonia, and then we have water, and because this guy acts as a base, then this one will act as an acid. So this one of these H's is going to pop off and go onto the base, which is ammonia. So the before there's 3 H's on ammonia, afterward there's 4 H's on ammonium. That's ammonium ion right there. And the water lost an H. Before he had 2, afterwards he has 1. So strong bases will have all of this happening, and it will break down into OH minuses on the right hand side, and they do it 100% of the time. Water can be together, and you have this in your drinking water all the time. You have a few of them are looking like this, and they react together, and that H+ pops off and goes onto that guy. So this guy is acting as the base, this guy is acting as the acid. So before he had 2, after he has 3. So he took that H+. Before this water has 2 H's, after only 1. So he acted as the acid, he gave that H+ to that guy. This only happens a little tiny bit of this happens, so just a little tiny bit react and do this, and they form this and this. So that's what you have in your drinking water. But it's a really small concentration. So we can figure out that water does this thing, and it happens all the time. And if we figured out the H+ concentration when this water broke down, and the OH concentration, we'd find it equals this number. So remember, brackets are molarity. So the molarity of H+, the molarity of OH minus, when you multiply them together, they always equal this number. So Kw is this number. So if you know this, and I give you one of these, you can figure out the unknown, one that you don't know. It's called the Kw, the ion product constant, and this is this number, and you need to know that number. So we could do calculations like this. If we know one, we can find the other. So if I know that H plus is 10 to the minus 2, and I know totally they have to equal that, then I know the other guy has to be 10 to the minus 12. So the pH scale is the log of that H plus concentration. So it's the log of this H plus. So once you find molarity of H plus, you just hit your log button in your calculator and you'll find the pH. And remember, pH always has to be a positive number. So acid things are between 0 and 6 or so, and then 7 is neutral. And then things that are 8 or above to 14 are basic. So here's some examples of things that are acids and bases that you guys know. And I'll do practice in class. And then when we have an acid and base, like the titration lab, we're doing something called a neutralization. And remember, that's when we use the M1V1 equals M2V2. If you see the word neutralization or acid-base reaction, you can use that M1V1 equals M2V2. So when we have an acid, which has that H plus, and a base, which has OH minus, they react together, they form a salt and water. So this is something you need to know. When you have an acid and base together in a neutralization reaction, you're going to form a salt and water always. So know that so you can do those kind of reactions. So we'll do practice. Buffers are a combination of a weak acid and its salt. So we have weak acids and weak bases together in a container, and it keeps the pH from changing. So it's really important in a lot of systems like our bodies to keep the pH at a particular level. So if we look at the picture of it, so we have things that can act like acids and things that can act like bases. And so if you add a base to this, it's going to grab that H plus with the OH minus and turn into water, and the pH isn't going to change that much. If I have an H plus, it's going to react with this guy and jump on there, and we'll get rid of it. So we can slash these and get rid of them out of the system. Because if you have too much H plus in your body, it's very acidic. It's not good for you. If you have too much base, OH minus in your body, it's not good for you. So if we have a buffer in our body, which we do, which if we have a different buffer, it's called carbonic acid, that can deal with any fluctuations in H plus or OH minus due to bacteria or your body messing up, and we can keep the blood at the right level of pH. Redox is the short name for oxidation and reduction. Oxidation means you're losing electrons. Reduction means you're gaining electrons. So oxidation means it's going to become more positive with the oxidation number, the little charge number up top. Reduction means you're going to become more negative. Okay? So in this situation, if you have an element all by itself, its charge is going to be 0. You don't see a charge at 0. This element is another element, oxygen all by itself, so it's going to have a charge of 0 up top here. Afterwards, this magnesium becomes a +2, because you guys know that from the periodic table. And oxygen's in group 6, so its oxidation number when it's in a compound is going to be -2. So Mg went from 0 to +2. So that means it gets more positive, so it's oxidized. Oxygen goes from 0 to -2, so it became more negative, so it's reduced. So work on these practice problems because there's a couple of these on the Unit 2 test. Precipitation means you're making a solid when you do a chemical reaction. So two ions, when they meet up in a beaker, they're going to form a solid, and you'll see a cloudy appearance in your test tube, and after a while that cloudiness will settle on the bottom and you'll see a solid. So that's called the precipitate. So there's a few ions that always like to make precipitates, like silver. Ag likes to do that. Sulfur likes to make precipitates. Calcium sometimes, and sometimes OH. Hydroxide likes to make a precipitate. So if you remember those, I think that will be good for you to remember those 4. So when we make that solid, we have ions in solution, Na+, and Cl- from salt. Then we have another beaker that has silver and nitrate in it. And when we put the two beakers together, we pour them together, then the silver finds the chlorine and they form a precipitate, the solid. That's what S means. And then the other guys are still in solution, they're just bouncing around inside the water. But the silver is going to settle on the bottom because it makes a solid. We also have heat going on when we do chemical reactions. Reactions either going to give off heat, which is exothermic, or it's going to take in heat, which is called endothermic. So if you ever use those heat packs when you go up to the snow to keep your hands and feet warm, those are exothermic reactions. You're putting two chemicals together and they're forming heat, which is good for your hands. Endothermic is like when you get a bruise or you sprain your ankle and you get one of those cold packs, you break the two chemicals and they mix together. They form a cold reaction, and that's called endothermic. And how much energy is released or gained is called enthalpy, fancy name for heat of the reaction. So if you have reactants that start off with a loss of energy and they lose it over time, that's exothermic. If you have reactants, you do the chemical reaction and you have to shove energy into them, that's called endothermic. The products have more energy than the reactants. The other thing we have to think about sometimes is how fast does a reaction happen? So some reactions will happen, but it takes forever for them to happen. So we can make them work quicker by either increasing the concentration of the two things that we're trying to hook up, or if we make the energy of those little particles moving around faster, which is heating, and that's increasing the temperature. So those two things can make things happen faster, make the rate of things happen faster. So this example is just showing, like, if I just had one red guy trying to bounce around with other molecules in there, the blue guys, if I have one, it makes it harder to get that chemical reaction to happen than if I have lots of reds and blues, so they can find each other, hit in the right way and with enough energy, and then form a product. So getting enough energy for these guys to hit together is called the energy activation. And if it's really cold in the beaker, then they're not going to have a lot. They're not going to be moving really fast. If you can heat the container up a lot, you can make them move faster, and they will hit in the right way and form the product. So up top here, they're moving kind of slow. They're hitting into each other. This is AB. This is one molecule. CD, another molecule. They hit. Oh, they don't hit with enough energy, so they just go back to the way they were. They don't rearrange themselves and find new partners. So there's not enough energy in this situation. But if I heat these guys up and make them hit into each other super fast, then they will start breaking the bond they had with each other and making a new bond with the other guy, and then they form new products. So if you heat things up, it makes things go faster. And so sometimes that's a bad thing in the body. If you have a high temperature, it's going to make reactions happen faster, and sometimes that's good and sometimes that's bad. So you'll see this on the Unit 2 test, these energy diagrams, and this is an example of exothermic reaction. The reactants have more energy than the products, so they lose that energy when they do the reaction, and it goes out into the surroundings, so you feel it as a hot reaction. So this part here is the initial energy of the reactants, and here's the final energy of the products. So if I ask you guys what's the energy overall of this reaction, you're going to take this minus products, and you'll get that answer. If I ask you how much energy does it take to start this reaction, that's called energy of activation, you'll take this number up here, whatever it is in the graph, and subtract it from reactants. So that's going to give you the energy of activation from here to here. So overall, reactants to products is the energy of the reaction. From here to here is the energy of the activation. And luckily in our body we have things called catalysts, which are enzymes, little proteins in the body that make things happen faster, and it makes this energy of activation smaller, so our body doesn't have to use so much energy. That's a good thing about enzymes. One of the last topics on the unit test is Le Chatelier's principle. It says that if you have a reaction that starts with reactants, goes to products, and then also likes to go back to reactants, so you have an equal amount of, you have some of these guys and some of these guys, and the reaction goes back and forth, back and forth, back and forth, bounces around like a tennis game. If you try to change that, the way they're going back and forth, if you try to change that by changing concentrations of reactants or products, the reaction will try to balance that and go back to the way it was. So that's the Chatelier. You disturb it, changes are going to happen to try to get back to where it was in equilibrium. And here's an example of getting to equilibrium when you're dissolving something in water. So if I throw a sugar cube in water and it starts dissolving and going into the water from the crystal, there's going to be a point where you can only put so much sugar in the water. And that sugar is going to say, hey, we're at that point now, so we're going to start bouncing, going back into the solid crystal shape again. So that, when we have that, the rate of dissolving equal the rate of crystallization, that's called the equilibrium. That's it for Chapter 7 lecture. And that's the end of anything you'll need to know for the Unit 2 test. So good luck on that test. I'll see you soon.